All right, welcome to today's Energy Symposium, sponsored by the University of Texas Energy Institute. Carrie King, research scientist and assistant director at the Energy Institute. Today, remind the students in the audience that next week is the first research note that is due. So you're supposed to write on some of the energy symposia that have occurred to this point, so that's due next week. Next week's talk will be Mike Sloan, who's a local energy consultant, energy and policy consultant. He's been around for a while and knows a lot of the history of energy policy in the United States, as well as specifically Texas. So he's going to give his perspectives on sort of energy policy in Texas and other places around the United States. Today we have Tim Siegler from the University of Texas here. He's a postdoctoral fellow that works in the research group with Dr. Brian Korgel, who runs the Center for Next Generation Photovoltaics. And so today he's going to tell us about, in particular, I suppose, next generation photovoltaic material, Perovskites, who he's now informing us is their 10th birthday of understanding, or at least the birth of these materials. So he'll tell us why it's the birthday and what the future is for this new type of material for photovoltaics. So thank you, Tim, for coming, and take it away. Thank you.
All right. Thanks, Carrie. Can everyone hear me through the microphone in the back? Okay, great. Thanks for everybody for coming to this talk on perovskites. Hopefully a good high-level introduction to people who may have heard the word perovskite around but don't actually know much about the material itself. Before I get started talking about why perovskites came about and why they might be a cool alternative or supplement to silicon technology, I want first everybody to spend about 10 seconds and picture in your mind what you think of when I say solar photovoltaic power. So, what comes to mind? What's the first thought? I imagine, for most people, you think something like this, where you have these really large, rigid, heavy, thick, inflexible eyesores that dot the roofs and abandoned cow pastures of all these different areas around Texas and southern United States, and as well as in Europe and other places. Some other things you may think of that you may or may not have thought of, depending on your familiarity with semiconductors, is that these materials also have to be perfect. In the current paradigm where silicon is king in the photovoltaics world, you're relying on a material that actually is a very, very poor absorber to convert sunlight into electricity. Given that the way a solar cell works is it absorbs light, excites electrons, and these electrons get extracted through an external circuit, that means that if you want to efficiently absorb light in a material that does not absorb light very well, you need a very, very thick layer of that material, usually about 100 microns to 1 millimeter thick, 100 microns, 100 micrometers. Now, to you and I, that might not seem like a very long distance, but for an electron that's excited by a photon of light, that is a super long odyssey that it needs to undertake. And along this odyssey, if it sees an atomic imperfection, a silicon atom that is out of place, a silicon atom that's replaced with something else, it has a strong propensity to just die on that spot. It's called being trapped in a defect site. And so part of the reason that silicon materials have been so expensive for a long time is that you needed to find a way to cheaply make materials that were perfect at an atomic level. And however, technologists, researchers, other material scientists were able to do this very well. And as of 2017, silicon is dominating the PV installation market with 96% of all installations globally in 2017, according to Fraunhofer. Part of that is due to the fact that these can make really efficient PV devices, but also just because it has a time advantage. People have been studying silicon technology for 50 plus years, and so it is currently king. The rest of the market is fighting for the scraps, or these thin film technologies, CAD-TEL and SIGs, which I'll be talking about a little bit later. And so the question that I think researchers who are cognizant of their impact on society are thinking is, okay, what does technology disruption then look like in photovoltaics? Not from a financial side, from a pure technology side, looking at the panel, what does technology disruption look like? And I think the old way of thinking, when you're competing against natural gas, you're competing against fossil fuels, it's all about cost reduction. Everything that you do is for cost reduction. And indeed, you can see as these costs tend to go down, installations worldwide, I believe this is, no, in the US, they tend to go up. And there's a very good correlation between cost and the number of PV modules that you can install. Things, you can do this from a technology standpoint by direct cost reduction. Now, just to explain this graphic here on my left, this is a sort of roadmap that Sunshot and the DOE, a Sunshot program, a subset of the DOE, made to drive the reduction of cost of a utility scale PV panel by a third between 2015 and 2020. It's just illustrative because you see that lower cost actually doesn't contribute that much. Just lowering the cost of manufacturing your PV panel doesn't do that much to actually lower the cost of your system. Things like efficiency gains and higher reliability can actually do a lot more. And so even things like making your panels more efficient and making them more reliable all serve the bottom line cost reduction in the end. But now we do have a PV market. Solar PV is becoming a more mainstream player by the day, and it's growing exponentially. So now that we do have a market, and we're not just competing against other types of electricity generation, what does technology disruption look like in photovoltaics now, in the next generation? And what I think it looks like is something like this, a flexible, ubiquitous type of application of photovoltaics, where you can buy these sort of shrink wrap panels at Home Depot. Now this company's out of business, so whatever. But you could buy these sort of flexible panels. You could peel off the backing, which has some 3M tape, stick it on your roof whenever you'd like, or maybe you have a garden hose sort of wrapping of solar panels that you can take a truck then, drive out, unroll your panels, reversibly retract your panels when you're done, when you need the field. Let's say you have a music festival that only happens on the weekends and you have just nothing during the week. You could maybe roll out a couple solar panels to fill that space and then retract it as the field is needed and not. Or maybe it looks like something you can fit in your pocket or backpack. A rollable solar PV, it looks like kind of a big battery. When you're working outside, on your laptop and your phone needs a charge, you can unroll it, put it on the bench next to you, and just plug your phone right in. Or maybe it even looks like something like this, a different kind of concept of a solar cell that is super inefficient, but is so cheap to make that it is actually disposable, where you can have single-use solar cells powering things like low power needs, like maybe food sensors, dynamic food sensors. So you don't have one milk label that says used by X date. I don't know if that's actually how it's going to be, but maybe it will be, maybe it won't be. Maybe you have a dynamic sensor that can tell you in real time how good your milk is, or things like that. And so thin film PV arose to meet this need. So thin film PV, the general idea is, well, why are we using a poor absorber to make an absorbing photovoltaic device? We should use a very strong absorber. That way we can reduce the thickness of our films from this 100 to 1 micron that I was 100 microns to 1 millimeter I was talking about earlier, and thin your active layer down to about 1 micron in thickness. This allows for more flexibility, not because the materials themselves are any more or less flexible, but just as you get thinner and thinner down to a micron or less than a micron, any material, everything being equal, will always have more lability to it. If you don't believe me, start chopping down a slice of wood and see how a thin slice of wood is more flexible than something that's fairly thick, like a board. The issue, though, is high temperature processing of a lot of these materials that's required for near perfect films has limited the application of a lot of these materials in flexible designs. Take, for instance, cadmium telluride, which is a material that is probably I'd say the most charged to compete with silicon. It's achieved fantastic metrics in terms of cost, in terms of efficiency. Note, for the remainder of this talk, I'm going to be referring to efficiency as PCE, to be more specific. PCE refers to power conversion efficiency, which is defined by the power of electrons out divided by the power of solar radiance in. It's just a shortcut, and it's easier to talk about. Like I said, it's more specific. Stability is very good, but again, 500 to 550 C, you can't really use it in a flexible design. And the reason is unlike silicon, when you have a really thin layer of a material, it doesn't do well standing by itself. It'll crack open all the time. You can't really use it as a standalone PV. So you need a substrate to back it on. And if you think about every flexible substrate you can think of, maybe plastic, maybe metal, all of these melt at 500 to 550 C. So you can't actually put these directly on a flexible substrate, and you have the same problem you have with silicon. So CadTel panels are, they have to compete directly with silicon. And to their credit, they've done a remarkably good job. First Solar can routinely win bids in PPAs in various areas. But nonetheless, you can't use it for this ubiquitous next-gen flexible PV. SIGs is a little bit more promising, copper indium gallium selenide, which has also arisen as a more recent material to try to meet this need in the thin film community. But even there, you have a annealing temperature of 250 degrees C, which means you need specialized plastics to act as your substrate backing, like polyimides. And that means that cost has been an issue for this material, let alone the fact that just the cost of making SIGs can be problematic as well. Nonetheless, there are people trying. The solar sort of garden hose I was talking about earlier, that's a real company, Renovagen, in the UK, that's trying to make flexible SIGs panels that can meet these needs. Their costs are still, like I said, out of control, but they have been able to have some customers in some high power, electricity market, like high electricity price markets. And so solution process PV came about to combat some of the limitations associated with these traditional thin film technologies. The idea was that material chemists would come up with solar inks. You could make your absorbing layer, instead of doing a direct deposition on a substrate, you could make it somewhere else in a solution or as a powder or something like that, and then deposit it from a solution process and therefore expose your substrate to very low temperatures, less than 100 degrees C in most cases. And you have more flexibility, and that's kind of a pun, because you have more physical flexibility, but you also have more flexibility in deciding how you're going to deposit your solar cell. You can do a variety of different things. You can spray it like spray paint. You can actually use a physical paintbrush. I've seen people do that. Or you can do a sort of spin coating process, which I'll talk about later. You have a lot of options when it comes to solution process PV in principle. Usually, though, this has come about with the trade-off of poor efficiency for these devices, for these types of devices. The first solution process PV that was come up with was invented by Michael Gretzel in 1991, and it was the dye-sensitized solar cell. And Professor Gretzel's idea was we have these dyes that we've known about since prehistory. They're really strong absorbers. We use them to dye clothing, other things, and they absorb light incredibly well. But they can't move electrons anywhere. So an electron gets excited and it gets stuck there. And so his novel idea was, let's take these dyes that absorb light super well, put them on a support that can transport the electrons, and so you have the dye doing the work absorbing and another material doing the work to transport the electrons through the external circuit. The issue, though, is because he was an electrochemist, he used a liquid junction interface. And so it's not a real practical design if you think about putting this in the field for 25 years. Your electrolyte's going to start to corrode, or it will directly evaporate. You'll have issues with that. And so it became a bit of an issue. It never actually got to high PCE. And additionally, you couldn't really use it in flexible designs anyway, not just because of the electrolyte issue, but because the TiO2 had a 500-degree sinter associated with it to get nice quality films. But the cool part about the dye-sensitized solar cell was not the solar cell itself. It was the idea that material scientists, chemists, material chemists, chemical engineers could come up with new, crazy, alternative designs to the traditional silicon panel that you see, which is just a big block of semiconductor solid. And to that point, a lot of different people did start to riff on this design to make their own types of PV designs. Some material scientists took the idea of a Gretzel cell, as we call it, and instead of using a semiconductor dye, said, well, we can make these things called semiconducting quantum dots. Now, these quantum dots are the same type of material, semiconducting material, that you would use in a regular solar cell. However, we can make their size very small and change some of their absorbing properties, as well as getting them to be able to bursts in common solvents like toluene, chloroform, or hexane. And by doing this, we can directly make a solution process solar cell using the Grätzel cell and get a better absorber, a more electron conductive material that could theoretically have much higher efficiency. Unfortunately, in practice, the liquid junction solar cell didn't really get to a very high efficiency, and it still had some of the issues of the Grätzel cell, although people who took this design and have made solid-state devices with quantum dots have actually gotten to a fairly respectable 16 to 17% efficiency. Actually, this year the record was broken again. So there's still some promise for this type of design. But it was around the advent of the quantum dot solar cell that people were trying to say, okay, we have really bad efficiencies. Where can we find new materials to put in this architecture that are going to, change things, make them better? And one researcher in Japan, Professor Tom Miyasaka, said that, okay, well, I have this semiconducting material, these methyl ammonium lead iodide perovskites, that I can dissolve in dimethylformamide. What if I don't want to make quantum dots using the traditional methods that people use to make quantum dots, hot injection methods and the like, but what if I can make a quantum dot solar cell by dissolving this material, putting it on TiO2, and just letting it react on the TiO2 and see what happens? And he actually was able to get 4% efficiency from the first trials that he performed in his lab. Now, 4% may not sound very interesting to people, but for a material that no one had ever used for solar applications, to get 4% on the first try, people were very excited and interested in this material. And again, this was in 2009, hence it is the 10th birthday of the perovskite solar cell. And so there was another challenge that was, I think, related to the low efficiencies, relatively low at the beginning, of these perovskite solar cells, is that perovskites would dissolve in seconds. These things were still using a liquid electrolyte. And so how they made these perovskite solar cells in the beginning is they first reacted the perovskite on the TiO2, they'd expose it to the liquid redox couple, and they would run as fast as they could to the solar tester to test these things before they dissolved within 60 seconds. So the obvious solution to try to fix this was to move beyond the liquid junction, to get rid of the liquid junction altogether, because it was very clearly a dissolution problem, and to use solid-state electrolytes in lieu of the liquid junction redox couple that had been used in a lot of years past. There had been a body of quantum dot and dye-sensitized solar cells that had used solid-state electrolytes, but they weren't very efficient, so it wasn't super promising at the beginning. However, the very first people to try got really cool results. Henry Snaith at the University of Oxford, though it did take him 300 to 400 tries, managed to get a solar cell with 10% efficiency using the solid-state electrolyte spiro-OMI-TAD that you can see here. This was wild because this was a time when there were almost no solution processed PV that got up to 10%. And here was the third paper in this field getting to 10% in a fairly benign trial. Even more promising, the fourth paper in this field, or third to fourth, it's an argument about who came first. Professor Namgyu Park at Sungkyunkwan Kwan University did a very similar thing with spiro-OMI-TAD, and by using very high quality TiO2 was able to get 9.7% efficiency on a relatively large area device. And material chemists, material scientists seeing this, people working in solution processed PV, they took to this very quickly and they said, oh, this is awesome. Let's try to make a more efficient cell, and it was off to the races after that. From there, efficiency just kept growing and growing. This data, it's the same data in the graph and the table, shows you the number of years after the invention of each type of PV technology it took to reach 15%, 20%, and 25% PCE. You see, normally for a material, it takes about 10 to 20 years to get to about 15% PCE. It takes another, 10 to 20 years to get to 20% PCE, and then most don't ever reach 25% ever, even in a small scale in a lab. But perovskites reached 15% within 5 years of being invented, only took 2 extra years to get to 20%, and now on its 10th birthday has achieved recently, I believe in September or August, got a certified PCE of 25% in a single junction device. And so the explosion of this performance, this efficiency performance, is off the charts and unprecedented in any solar material. Today, perovskites are the third highest standalone, own the third highest standalone PCE of any PV technology, second only to silicon and very expensive gallium arsenide cells. There are currently, there's a huge amount of effort in the academic community, lots of active research in this area. There's about, I'd say, 30 to 40,000 publications if any of you are very interested and need some further reading in this area. And there's a burgeoning startup community as well that I'll be talking about a little bit later. And it's received a lot of media attention as well. Green Tech Media has talked about it, and Forbes has also featured it several times. And I really like this talk from Mike Scott at Forbes, because I mentioned how precipitous or how exponential the rise of perovskites has been, how quickly we've developed this technology, and yet perovskite solar cell technology, which has the potential to make solar panels more efficient, has been stuck in the lab for a number of years. So maybe we're going really fast, but maybe not fast enough for some people. That's okay. So the question many of you may be asking is, this is all cool, this is all great, but what is a perovskite? The most simple answer to that question is it's a mineral that has very little to do with solar. It's calcium titanate. It was found in the Ural Mountains in the late 1800s, late 1800s. But like most materials that were discovered at that time, material scientists who did discover it were able to, using X-ray crystallography, determine the positions of each individual atom in this structure. And it was such an interesting arrangement, these nice cuboids, that they decided to call any material that had the same atomic structure as this mineral perovskite. And so even though our materials are very different than calcium titanate, they have nothing to do with calcium titanate, we call our materials perovskites because they have the exact same atomic structure that you see here. These nice little cubes that have these different types of geometric bonding. And so our perovskites, instead of using calcium, have an A site that is usually an organic cation. That's why you might hear them sometimes referred to as hybrid organic-inorganic perovskites, because they have an organic component, and it is usually a carbocation that is put in the A site. That's usually because most inorganic cations are too small to fit in that A site, so you need something fairly large, like a multi-atom cation, to fill that space. The B site is usually lead, but sometimes tin. And the X site is not oxygen, but rather something in the halogen series, chlorine, bromine, or iodide. And these are the types of perovskites that people used for are still using for classic fundamental studies, methyl ammonium lead halides like methyl ammonium lead iodide, methyl ammonium lead bromide, or the formamidinium lead halide series like formamidinium lead iodide and formamidinium lead bromide. And they're often referred to by their abbreviations that you can see here. So if you see these anywhere, you also know where that comes from. And so the question now is, okay, so I know what a perovskite is. I know what they can do. Why perovskites? Why not something else? Why did this material tend to sort of win among the academics? Well, the first thing that may appear trivial, but is actually super non-trivial, is that the bulk material of perovskites can dissolve really easily. Think of the types of PV technology that you are familiar with: silicon, cadmium telluride, copper, indium, gallium, selenide. These materials can't be dissolved unless you use incredibly difficult, corrosive, and really dangerous solvents. But methyl ammonium lead halides, formamidinium lead halides, all these perovskites can dissolve in very common lab solvents like dimethyl formamide and dimethyl sulfoxide, which means that we can use them and actually process bulk materials, not just nanomaterials, but bulk materials of these semiconductors from solution in a variety of different ways. They also have very good defect tolerance. I mentioned at the beginning of the talk, in silicon, you have these electrons, and they don't like seeing atomic imperfections. In perovskite, not only do you have a much thinner film where these electrons don't have to travel as long of a distance, but you have, when an electron encounters one of these atomic imperfections, either the atomic imperfection is not energetic enough or too energetic to personify it a little bit, to want to take the electron, or the neighboring atoms that are next to the imperfection screen the electron, try to get the electron to move away from this imperfection. So this is what we call defect tolerance, and it allows us to make really, really, to be honest, really bad films and still make really good devices out of these really horrible films. And then color tunability has also kind of made the application space for this material really large. This is not only the red, green, blue, orange color space that we're familiar with, but also the ability to change the color in the infrared range, in the near infrared range, has proved really useful for a number of different applications. But some of the major issues, some of the things that make this material special can also be its downfall. The fact that the bulk material dissolves well means that it can dissolve in really cool solvents like DMF and DMSO, but that it's also susceptible to water vapor-induced degradation, and it's very unstable in humidity, as well as some other types of stimuli as well, like high electric fields. And then I think the other major issue that has been plaguing commercialization of this technology is that the best lab methods aren't the best industrial methods. So the ways that we deposit these really nice, super efficient thin films in the lab is not necessarily a super scalable process that can be used by industry. To prove the point on the perovskite degradation, here are some photos I took before and after 72 hours of aging at 90% relative humidity for a recent paper I published. The perovskite films, when I first make them, are nice, dark black films that you can see here. But within only 3 days of aging, they turn into these useless yellow and white films of nothing. And so one thing that I did to try to help stabilize the perovskite is I tried to see if I could do some heterovalent incorporation, so some incorporation, replacement of the lead with a little bit of bismuth to see if that could stabilize the perovskite thin film. We were able to see that at high relative humidities, we could stabilize the perovskite thin film. The way I know is because the absorbance between this point here, and this is just a simple UV-vis absorbance curve. You can remember it from high school chemistry, maybe you don't, but that's okay. We want this curve to be high in the region between 525 and 750 nanometers, and that tells us you have perovskite, and then when it goes down, the perovskite also goes away. So essentially, don't worry too much about that. This is telling us the bismuth has stabilized the perovskite by about a factor of 3 at high humidity, which is very promising. But then we took that down to 60% relative humidity, did the same test, and we saw the opposite effect. This stabilizing and destabilizing effect was the first report of its kind in the field. And I believe that it's important for anybody who's trying to age test or warranty perovskites. The startup community is getting closer and closer to having commercial products. They're trying to get warranties on them, and they're using silicon aging tests, which involve an 85 degrees Celsius, 85% relative humidity aging as a time accelerant. And I don't think that is necessarily good, given the fact that additives can have this disparate effect above and below a certain threshold, about 75 to 85% relative humidity. In fact, another paper that we were able to show that a related material was so unstable in humidity that the reversible water uptake of the black thin film could be used as a smart window material. Taking a black film of nickel iodide, which is not by itself a perovskite, but it's chemically related, out of the glove box where I was a controlled nitrogen environment where I synthesized the thin film, you can see that really quickly, within 2 minutes or so, it turns first into this white solid, and then then after about 5 minutes, turns into a white liquid that's mostly water, that you can see there. But unique to this material versus what perovskites normally do, you can actually take the white liquid, the water liquid that precipitates on the film, and you can revert back to the dark phase of the material, the nickel iodide. And so this could potentially be used for energy efficiency applications with smart windows that require sort of color neutral transitions between completely clear and completely black states. The scalability concerns have also been an issue. So this is what a spin coating process looks like in general. Essentially what you do is you take your liquid precursor, your solution that you're going to process, and you spin it really fast. And this has the result of forming a very uniform, very thin film. And that's really great for making devices at a very small scale. But imagine taking a meter by meter squared square of anything and putting it through the similar process. It's not necessarily the best way to try to make very large area solar cells. One thing that we did in our lab to try to maybe help this out a little bit was another paper I recently published where this isn't an alternative to spin coating, but I was able to add a little bit of silver to methyl ammonium lead bromide perovskite and show that I could, in so doing, create thin films that were atomically very well ordered. All the crystals were pointing in the same direction, which is kind of hard to do. And so hopefully this could help mitigate some of these issues, though it won't necessarily solve them. And so what's the state of the art? Beyond my lab, beyond what I've done, what is the state of the art for stability? So there's multiple reports of in the literature of perovskite solar cells that have 50 days of continual operational stability. It doesn't sound like a lot, but think about it in terms of me, the researcher. I don't want to be aging my films for more than 50 days. I want to be able to publish, hopefully this year. So when I say 1,200 hours of continuous operational stability, I don't necessarily think that that's a big problem, especially given the fact that a lot of these PCEs can indeed pass these IEC accelerated aging tests I was talking about earlier, where they, which is the way that you warranty a silicon panel in the industry today. Furthermore, there's even a startup that on their website claims that they can have 25-year warranty level stability in a mini module, though I also don't see any 25-year warranties being offered by the company at this point, so maybe I'll wait and see on that specific claim. Scale-up has had, I think, even more success in terms of where we were 5 years ago versus where we are today. I would even say this isn't an issue anymore. So this is a video from Sala in Poland, where they, instead of using a spin coating process, have a completely automated high throughput deposition. Now this is an incredibly intimidating video for me, a person who makes these tiny solar cells in the lab that are about this big, spin coating, and then I see this robot making about, I want to say, a month's worth of solar cells that look incredibly good, trust me, on that one, in a matter of 30 seconds. So there's been a lot of work on the scale-up process, and maybe that's not necessarily an issue anymore. Cool, so this is great. I told you a little bit about the research about perovskites and everything, but where's the market? Where can perovskites fit? Because after all, silicon is still king. It's still dominant. It's still more efficient for now. It won't be probably in 5 years, but I think for now it's more efficient. It's beating fossil fuels on price by itself in many markets. So, a lot of people might say, well, we don't need a new PV technology if silicon is already doing very well on the cost side. And additionally, developers are very comfortable with silicon. So how are you going to convince them to change their comfort zone to a new material? And I think there's a couple different paths you can take. I think the first one is kind of like a cowardly path, is to say, no, we're not going to compete with silicon. Perovskites and silicon are better together. This is a tandem solar cell type of architecture. The idea being, in an individual solar cell, you can only get up to 34% efficiency. And this is because you have a trade-off between the amount of solar spectrum you can absorb and the energy that you can extract from each individual electron you generate. But if you pair two materials in a tandem architecture like this, with different absorbing properties, you can raise this fundamental thermodynamic limit to a higher value and potentially get more bang for your buck and some cost reductions as well. The fact that perovskite can be deposited at less than 100 degrees C means that you can do what we call a monolithic integration. So you can double the amount of solar cell you have without doubling things like the interconnects or the the balance of system costs, the sort of soft costs associated with hooking these things up electrically that you would normally have. And indeed, this is the actual quantitative efficiency jump that you can get from 34% up to 42% with a silicon perovskite tandem. And so 30% modules in such an architecture is not necessarily something that's unrealistic. We, in our lab, did a little bit of work with the Wilajebat Sampath group at Colorado State trying to make perovskite CadTel tandems, given that CadTel is the second largest market, PV market that we know of, and that there's a large body of literature on perovskite silicon, but not a lot on perovskite CadTel. In fact, there was almost nothing on perovskite CadTel. So we did some design on what a prospective perovskite CadTel solar cell would look like. We constructed some initial cells that were pretty poor in performance, but we also were able to use some of these results to simulate what a perovskite, this is a wider bandgap perovskite, so 10% PC is actually quite ambitious with this specific material, but nonetheless, it's the simulation of what the sort of performance metrics of a perovskite solar cell would be to pair effectively with CadTel. The second path is to do things that silicon can't, or at least things that they can't do very well. You can either make a permanently flexed design, such as this building integrated PV. I personally think this is a pretty funny mock-up here, because you look at this, I think it's about 3 stories tall and wrapping around the entire building. That's a huge solar panel to try to put up there. But permanently flexed designs that are similar to this at a smaller scale are something that silicon can't do very well, and potentially could be fit by a niche that could be fit by the perovskite community. It's called building integrated PV. Additionally, variable flexible solar cells like this on my left could be used to try to fulfill some of the promise of ubiquitous solution process PV that I mentioned at the very beginning of the talk. And indeed, startups are kind of going down one of these two paths. The two biggest startups that I see in the industry right now are Oxford PV, a very large high valuation company in Oxford that's nominally working on perovskite standalone PV, but I think is exclusively working on silicon perovskite tandems. They actually own the record, the efficiency for a silicon perovskite tandem PV, which marks the first time that a solely commercial entity has owned such a record. They're very serious about trying to pursue these tandem PVs. They're the ones who made the warranty claims that they have 25-year operational stability. I think that they're a huge tour de force to be reckoned with, and it's very interesting to see how they're going to proceed going forward. And then Solid Technologies, which is responsible for that YouTube video I showed, they're trying to work on the other aspect, flexible PV, building integrated PV. They recently signed a contract with a hotel in Japan. It's a high-tech hotel, but still it's a hotel in Japan to make building integrated PV for some of their new facilities. So that marks the first contract for building integrated PV for a perovskite solar cell. Additionally, they're launching all these pilot products like car chargers, like a tarp that would go over your car, furniture, all these different types of consumer products that people could buy perovskites in those as well. Additionally, there's a bunch of small players that have recently emerged from incubators. They entered incubators in 2016. They're now emerging from them, and they're going to try to start playing in this space as well. A lot of them are run by really smart people. So I do think there is some room for perovskite PV. And even if it doesn't work out for the PV side of things, perovskites are doing some pretty outstanding things outside of PV as well. They make really great LEDs, particularly blue LEDs. So anybody who's familiar with LED technology knows that traditionally making a efficiently emitting blue LED has been quite difficult for people. So perovskites could potentially rise to meet the need for different types of LED applications. Maybe your next, or maybe the TV after your next one is going to be a perovskite TV instead of a quantum dot LED TV as you see today. They could also be excellent photodetectors for Internet of Things applications. They're fantastic radiation scintillators. In fact, I predict that if a radiation scintillator, I predict that every radiation scintillator by 2050 will be made from some kind of perovskite material. They're good. They're okay photocatalytic water splitting absorbers. They have some interesting spin properties, and they can be used as gas sensors too. And so that brings us back to, will perovskite PV ever grow up? The question I posed at the beginning of this talk. And I think the answer is yes, but I don't think they know what they want to be when they grow up quite yet. Perovskites can either pair with silicon for 30% efficient modules. They can be a partner in PV. They can be used in flexible, permanently flexed, or lightweight designs where silicon can't really compete or do well. Or they can be used in a variety of different types of optoelectronic and other material science devices, LEDs, scintillators, things like that. And then maybe some of the expertise on the material side could be then translated to PV later on. So with that, I'd like to acknowledge everybody who helped me make this talk, Dr. Korgel, all my group members, as well as group members of the Milliron group who I collaborate with quite closely, all my funding, including Equinor, as part of the Next Generation Photovoltaics Center and the DoD, and then Walaj Abad Sampath and Tushar Simpi who helped me with cadmium telluride work at Colorado State. So with that, I'd like to thank everybody for showing up and asking me any questions.
All right, everybody knows to go invest in radiation scintillators now. It's going to be a gold mine of money. Any questions about this? I thought this was a great talk and a mix of detail, chemistry, and high-level information about how to perceive these and sort of the technology advancement space. So that was pretty good. No, wait.
Wait for them.
Okay, hello. Could you go back to the slide that has the smart window demo there?
Oh, the nickel iodide one?
Yeah.
It's a video.
I didn't quite catch the connection between the perovskites and this material.
Yeah, it's kind of tenuous, that connection. I was trying to make a new perovskite with nickel, and ultimately it didn't exist thermodynamically, but this is a related material. I think it's related because it's a near IR semiconductor with a halogen anion. So this is just something I was told also to highlight some of my work. This is some of the work that I think it's fairly interesting and sort of highlights the varied applications of perovskite inspired materials. So, yep. Yeah.
It's not 100 degrees centigrade that you have to get the material to turn dark.
It actually turns dark at like 50. So.
Okay.
Yeah. We did more careful. This is just a video. So.
I know.
Yeah.
So when thinking about where to deploy like perovskite technology, is it important to take into consideration like average low relative humidity locations?
Yeah, I think that's an interesting, ideally no. Ideally encapsulate them and stabilize them to the point where it wouldn't matter that much. But I do think as a practical consideration, they may find more success in arid climates, I don't know, Arizona, West Texas, things like that. I think it might be better suited for those types of environments, at least at the very initial stages. But like I said, the way that you would try to fix some of these issues is not just change the material, and people have changed the material to great success, but also find really great plastics or glass that you can use to trap the solar cell, control the internal environment of the solar cell, make sure that there's no water that gets in there. Or, so.
Thank you.
So it's great that you're not only focusing on the technology, but also the market segments.
Yeah.
But can you describe more about the levers you have? What's the long-term durability requirement to be commercially successful? And is there a lever you can pull to give that durability and trade off efficiency or trade off cost? Or is it just, it's not there yet in terms of, it can be there for cost, but it just hasn't got the durability for the number of years commercially? Can you give us some idea of the levers there and
Yeah. So there's a lot of compositional levers, and a lot of them are actually not trade-offs. So the perovskites that you see today are not very neat, like methyl ammonium lead halides, like I'm talking about. They're alloys of 2, 3, 4, 5, or even 6 perovskites together, because doing so gives you both. It gives you more stability and better efficiency. I think the main issue right now is, you can put these perovskites that have been traditionally, where their counterparts that are less efficient or less stable have been traditionally unstable in humidity. You can put them through all these different tests that take, a day, 2 days, 50 days, something like that. But I think it's a big unknown right now, the stability at the moment. I don't know, because of how new this technology is, I just don't know how perovskites are going to react when they're put in the field. And I think part of this is the fact that they degrade in a much different mechanism than silicon. And so trying to perform these tests, which are optimized for silicon on perovskites, I don't think is very instructive. And so that's what I think is the main problem.
Wouldn't you just create a bunch of prototypes and put it out in the Arizona desert and let it run for a few years?
That's what I would do, absolutely. But I think there's a little bit, for sure, especially in the Arizona desert, there should be no problems. But yeah, like I said, and there are people who are doing that. Like Oxford PV is currently, working to make these modules that will be doing that sort of thing, putting them in practice somewhere, putting them down somewhere. But yeah, for me, I'm still a little bit. I'm just going to say it'll be curious to see if they can reach these stability metrics that the startups have claimed they can reach. So yeah.
Then, I've read about, studied about triple junction for space applications where cost is no object, and I think you talked about sort of dual. Could you do a triple junction further and capture more of the spectrum?
Yes, you could. And I think that would be really useful for space applications, not just for efficiency, but because you can maybe make these materials really lightweight too. So you talk about launching things up into space, that's a huge concern, is the weight of these solar panels. The issue though is if you use any organics at all, any of these organic cations in the vacuum of space, they off-gas. And so you have stability concerns in that respect. But there are a bunch, including our group, Dr. Korgel's group, we're working on trying to make fully inorganic perovskites, which are uniquely stable as nanocrystals, which is a wild metric. That's a different talk for a different day. But there has been a little bit of work trying to make completely inorganic perovskites specifically for that purpose, for space applications. So.
I guess I will ask, maybe if you can explain a little more clarification. You were kind of hinting at it there in terms of the stability problem. Seems to be absorption of water. Yeah. Absorption of water, so you're linking to inorganic. So what is it that it absorbs water and shorts out the circuit, so to say, or it fills in spaces in the molecule in the material, or is there more you can say about why water causes it to degrade?
Yeah. So because you have so I'm gonna say hydrogen bonding. I hope that people understand what that is. Because you have an organic group in there, and the organic group is positive. The water wants to take the positive charge from the organic group, and in so doing, the organic group becomes a gas and goes away. And so it's a completely change of the phase. So you have a non-perovskite. Like once you expose these perovskites to humidity or water, they are no longer perovskites after you're done, after they're done degrading. So, yeah.
Hey team, thanks for your talk.
Thanks, Felipe.
So with respect to the degradation, so based on what you just mentioned, it only affects the organic part, because I guess my concern is for the inorganics, because some of these elements that you are using are like lead, for example, if those could degrade into the environment. So then it seems that would not be a concern. It's just the organic part that could.
Yeah, and there's a couple studies that have focused on this. They focused on, okay, if we have a perovskite solar panel on a roof and there's a catastrophic failure, and then let's say it starts to rain, will perovskite run, or will the lead part of the perovskite run off into the groundwater? And what they find out is the lead is fairly insoluble. So whatever degradation occurs, and whatever environmental exposure risk that you might have in the perovskite, once it's a perovskite, the lead is the part that's going to stay behind, and everything else is going to run off and potentially have some exposure risk. But it's all organics or halogens, so it shouldn't be that bad.
Cool.
Yeah, thanks.
No, all right. So I guess we have no more questions. So let's thank them for, I thought it was a very educational talk. Very good.